Bonjour à tous. Donc, c'est avec plaisir que je vais introduire la soutenance de thèse d'Emma. Donc, je vais commencer un petit peu en français par présenter le jury, puis ensuite, il va falloir switcher en anglais. Désolée pour les francophones. Donc, je vous présente les différents membres du jury. Donc, d'abord, je me présente, je suis la présidente du jury, je m'appelle Marie-Christine Angonin et je travaille à l'Observatoire de Paris et je suis professeure à Sorbonne Université. Donc, les différents membres du jury sont d'abord les rapporteurs, Pierre Vernazza, qui est chargé de recherche à l'Université d'Aix-Marseille, Enti Pentila, qui est chercheur à l'Université d'Helsinki, Madame Anna Mililo, qui est Prime Researcher à l'INAF à Rome, Monsieur François Poulet, qui est astronome à l'Université de Paris-Saclay, Madame Kerry Donaldson Anna, qui est en ligne et qui est Assistant Professor à l'Université of Central Florida. Et puis les co-directeurs de thèse, Alain Doris-Sundiram, qui est astronome à l'Observatoire de Paris, et Sébastien Besse, qui est chercheur à l'ESA. Et donc, now we can switch to English. So I introduce your defense on the volcanic and space-weathered surface of Mercury, spectral properties and the geological evolution that you have made in Lysia. And now I'll give you you can present it and we will ask you questions at the end. Thank you.
Thank you. So good afternoon, everyone. Thank you for being here today. I will present the work I did during my 3 years of PhD here at Lysia under the supervision of Alain Doris-Sundiram and Sébastien Besse. So my work is about the volcanic and space-weathered surface of Mercury using the spectral properties of the surface to better understand the geological evolution of the planet. And here I draw your attention briefly on the map that you can see, which is a false color images took by messenger. And the difference of color highlights different properties of the surface of Mercury. So my work is part of a better understanding of our solar system, especially about the processes that govern planetary evolution. And I work on Mercury, which is a very specific target because it's the smallest and closest planet to the sun. Moreover, the surface of Mercury is mostly volcanic in origin and also heavily cratered in appearance similar to the surface of the moon. The planet has a very tenuous exosphere and also a magnetosphere created by an internal magnetic field. So for all these reasons, Mercury is very interesting, and also because there is a very strong correlation between the interior, the surface, and the impact of the environment of the planet. And working on Mercury allows us to better understand the solar system formation in general, also to study bodies under extreme environment, doing some comparative planetology, and also help in exoplanet research. And here I put you images of Mercury took by Bepi Colombo during the 4th flyby a few weeks ago. So I will start with an introduction of the planet's surface properties. So Mercury was visited by 2 NASA missions, the first one being the Mariner 10 mission that performed 3 flybys of Mercury and imaged 45% of the planet. So among the main results of this mission, we discovered some very important tectonic features. And also we developed the idea that the surface was potentially volcanic. However, it's only with the second NASA mission, the Messenger mission that performed flybys, but also an orbital phase, that we had confirmation that the surface is mostly composed of lava. And nowadays, the exploration of Mercury continues with the ESA and JAXA Bepi Colombo mission, so the European and Japanese Bepi Colombo mission. Okay, so I mentioned that almost the entire surface of Mercury is volcanic, but what is volcanism? So volcanism is the eruption of a magma onto a surface, a magma which is produced by partial melting in death in the planet. And so like that, we understand how we can have access to the internal properties of the surface by studying the surface of volcanic crust of Mercury. Mercury has a prolonged history of both effusive and explosive volcanism concentrated within the first billion of the planet history and with a putative longer period. Here, I propose to compare on Earth and on Mercury two different types of volcanism. So you can see on the left, explosive volcanism on Earth, which is dominated by gas. And on the right, you can see pyroclastic deposit on Mercury. Here it's a false image color to show you the spectral properties associated with this explosive volcanism on Mercury. But in this work, I will focus on effusive volcanism. On Earth, you can see that effusive volcanism is like dominated by lava flows, like in Hawaii or Iceland. And on Mercury, the equivalence of this type of volcanism is this smooth, very less cratered plain. So about this smooth plain. So the surface of Mercury, even if entirely volcanic, was after its formation battered and fragmented by impact crater. So we used the number of impact crater to date the surface. And you can see here two different geochemical units on Mercury. On the left, the intercrater plains that cover around 70% of the surface. And on the right, the smooth plains that cover around 27% of the surface. So the smooth plains, they are basically the youngest large-scale effusive volcanism on Mercury. So to stay with the smooth plains, so they cover 27% of the surface. And here, please focus on the pink smooth plains that are volcanic in origin. And we can see that there is a heterogeneous disposition of the smooth plains. They are mostly located in the northern hemisphere, but also inside and around some major impact basin, like here around and inside the Caloris Basin, or in the southern hemisphere here within Rembrandt, or here within Tolstoy. So in addition to morphological units, the surface is also classified according to the composition of the surface. So the surface is magnesium rich and iron, aluminum, and calcium poor. Here you can see a map of the content in magnesium obtained by Messenger, and you can see how heterogeneous is the surface in composition. The composition of the surface was used to define some geochemical units that are represented here. And these geochemical units are also used to extract the mineralogical properties of the surface, which help us, for example, to identify some terrestrial analog to the surface of Mercury. So in addition to the morphological and compositional units, the surface was divided into different spectral units. From the darkest to the brightest, you have the low reflectance material, which is defined around the Rachmaninoff basin here with this dark blue units. Then you have the low reflectance blue plane defined around the Caloris basin here. You have the intermediate plane within the Rudaki planitia here, and the high reflectance red plane within Caloris here. We also have some minor units like the hollows or the fresh crater that help us to study space weathering on Mercury. So about space weathering, it regrouped different processes like micrometeorite bombardment, cosmic and solar ray, solar wind implantation that will alter the chemical, physical, mineralogical, and spectral properties of the surface over time. And this will introduce bias in the interpretation of orbital data, because when we study the surface of Mercury, we have a cumulative effect of heating, space weathering, composition, and so on. So on Mercury, it's a bit different than on unmagnetized body like the moon or a small body because of the presence of the magnetic field. So here I will not go into much detail, but it's just to show you that the magnetosphere of Mercury is heterogeneous and will lead to heterogeneous space weathering and precipitation on the surface. For example, you can see that we have the north and south cusps here and here that are open magnetic field and allow more precipitation on the surface. Moreover, I will just highlight how important it is to understand the correlation between the surface and the environment, because we see that we have the sodium group here that are influenced by the interaction between the environment and the surface. So here is just a bit more detail. So it's a map from Lavorenti et al. 2023 showing the proton precipitation on Mercury. And we can see that the proton precipitation is heterogeneous with latitudinal and longitudinal variation. So we expect different precipitation on the surface and so different intensity of space weathering. So now that I introduced the planet and its properties, I propose to focus on what are the history and mechanism of crustal formation and effusive volcanism, but also what's the relationship between impact cratering and magmatic eruption, and all of this to better understand the magmagenesis process on Mercury. And for that, I propose to study the Caloris basin and also to perform comparison between major impact basin on Mercury. However, I also mentioned the importance of space weathering. So I propose to study the space weathering regime on Mercury to better understand the spectral property considering the interaction with the environment. And for that, I propose to study the spectral alteration induced by ion irradiation on Mercury terrestrial analogs in laboratory. And of course, all of this to prepare the future ISA-JAXA Bepi-Colombo mission. So now about the methodology. So I use reflectance spectroscopy. So here I will introduce reflectance spectroscopy. So reflectance is the ratio between the reflected light and the incident light. It's sensitive to different different things, the composition of the surface, but also the physical properties of the surface, the geometry of observation, and everything related to the environment, like extreme temperature and space weathering. I will add more information about the composition. So here you can see on the top an olivine and on the bottom pyroxene. So you can see when we compare the two different minerals that the spectral properties are different. We have different spectra with different absorption bands. And moreover, when we compare only one mineral, like if you focus on the top, on the olivine, you can see that even for one mineral, here you have two forsterite that are magnesium pole of the olivine, and you can see that the spectra are different. And this is due for this case to the content of the iron content. So we can even have access more than mineralogy, we can have access to chemical property of the sample. So I will also briefly explain space weathering. So here you have M-cube data, so there are data on the moon. And you can see the difference in spectral property between a fresh surface, a crater, and a more mature soil in red. And we suspect that this difference in spectral properties are due to the formation of submicroscopic iron particles that are nanophase metallic iron form due to space weathering. And this submicroscopic iron particle can have different size and they will have different spectral alteration according to the size. For example, what I call the nanophase iron, which are below 50 nanometer, will darken and redden the surface. It's what you can see here on the moon. However, when they become bigger, and we call them Brit-Peters particle, they will darken without reddening the surface. So here you can see Mercury spectra. On the left, you can see old unit on Mercury, and on the right, you can see young unit on Mercury. And if you remember the spectra that I just show you here, you don't see absorption bands. So we have different theory to explain that. The first one being probably the lack of iron in the crust, or space weathering, or the presence of opaque and dark material, or the grain size, or even measurement limitation that we have for now. So to analyze this spectra, we develop some spectral parameters. We use, for example, the reflectance, but also the slope. And one parameter, which is the curvature, that characterizes this shape of the spectrum from the visible, from the near infrared, from the near UV to the visible here, because you see here that you have a way more curved spectra than here. We can do reflectance spectroscopy both in laboratory or with orbital data. So in the laboratory, it's a very powerful tool because it's allows to separate different processes that are accumulated in space. And so it helps to better understand the surface properties. For example, we can decouple the effect of the graphite content on the surface. Here, it's a study that analyzed for analogs of mercury, the effect of the graphite content. And you can see that when we change the content in graphite, we have different spectral properties. But in addition to the composition, we can also perform laboratory experiments to test the effect of space weathering on the spectra. So here it's a study that analyzed on an olivine, which is also an analog of mercury. And you have different irradiation dose from the A spectra here and the E spectrum here. And you can see that the properties are altered with ion irradiation. And it's also the case in the mid-infrared here, where you can see before and after ion irradiation, and you see that the spectral properties are also modified by ion irradiation in the mid-infrared. So as I mentioned, we can also do reflectance spectroscopy using orbital data, and especially in my case, using the messenger mask spectrometer and the visible and infrared spectrometer that can allow us to obtain spectra from 300, 1,450 nanometers. We can use the full range of this instrument composed of two different detectors, thanks to the correction by Bess et al. 2015, that allow us to have corrected spectra and have the full range of the spectra from 300, 1,450 nanometers. And this data, so the raw data, so the spectra not corrected, plus the corrected spectra are contained in the Mercury surface and spectroscopy database. In addition to this spectra, in the database, you also have a list of spectral parameters already calculated for each spectra, so each footprint on the surface of the planet. So it's a very useful tool to easily study the surface of Mercury. So now I will move to the first part of the result of my work, studying the calories basin. So here I quickly remember that the objectives to study the calories basin is to focus on the history and mechanism of crystal formation and effusive volcanism, but also about this close link between magmatic unit and impact crater, and all of this to better understand the magma genesis on the planet. So for that, the calories basin. So here I show you the calories basin. You have in full line the rim of the basin, and in dashed line, it delimitates the exterior volcanic plain, which is associated to the basin. So you can see that it's more or less 1/4 to the northern hemisphere of the planet. So it's a very important features. And what we learn around this basin can be then extrapolated to the planet to reconstruct the entire volcanic evolution of the planet. About this basin, so here you can see in the false color image that, so we see two different planes. If we consider a morphological point of view, they are both smooth, volcanic, and they more or less have the same age. Crater counting couldn't separate them in age. However, they have different spectral properties. So I wanted to understand what is the relative age of the interior and the exterior of the calories basin, and how to explain their spectral differences. For that, I developed a methodology. So I sampled 3 different spectral units: the low reflectance material that I show you, these very dark units, but also the interior of the basin and the exterior of the basin. And for each area that I sampled, I did a statistical analysis. So I basically calculated the average value of the sampled area and the standard deviation. And I created some framework that you can see here for one spectral parameter, that is the reflectance at 750 nanometer. So for example, when we sample the surface of Mercury, if the footprint has a reflectance at 750 nanometers between 0.026 and 0.031, it belongs to low reflectance material. And here, so I did that with two different levels of confidence. The first one with 100% of the data that I sampled, and the second one with only 50% of the data closest to the average to avoid to include extrema in the statistical analysis. And here is just the list of spectral parameters that I use. I just put the reflectance, but I also use several other spectral parameters. However, when we analyze the capacity of the different spectral parameters to separate the unit and to distinguish the unit, we see that they are not all efficient in the same way. For example, the visible slope will allow for a very better separation of the unit than the visible to near infrared slope. So if you look at the dashed line, you can see here that we can separate the low reflectance material from the low reflectance blue plane. However, when we look at the visible to near infrared, we see that it's harder to separate the two of them here. So I created a quality parameters to give more importance to certain spectral parameters than to other. And unfortunately, I will not have the time to develop the quality parameter now, but you can find it on page 88 of the manuscript if you want to check. So here it's the result. So it's a box on the surface of Mercury around the Caloris basin. And you have all the footprints of mask with different colors. The blue are the low reflectance blue plane, the white, the low reflectance material, and the red, the high reflectance red plane. However, this area, this little box, was used to sample the low reflectance blue plane, so the green one. So I expected the box to be filled by green footprints to be sure that I sample in a good way in a representative area. And here it's not what I see. So I removed the red and white footprints and repeat the statistical analysis without this contamination to validate the head member and improve the methodology. And so here it's exactly the same table than before, but with this new framework after removing the contamination. Okay, so now let's move to the results to see if the method is efficient. And here is the Caloris basin with the footprints on it that are classified. And you can see that the method allows for a very good distinction between the interior planes and the exterior planes. Moreover, when we zoom on this little crater that is called Adget, we can see a specific distribution of the units. So concentrated within the basin, you have low reflectance material. Then the low reflectance material here is surrounded by low reflectance blue plane in green, and finally surrounded by high reflectance red plane in red. And when we study crater, we know that the closest to the sample the unit is, the deepest the origin, the layer at the origin of this unit is. So we can easily reconstruct the stratigraphy below Adget and so below the Caloris basin. And here is what I proposed. So a first layer of low reflectance material, followed by two different volcanic infield, one of low reflectance property and one of high reflectance properties. So to conclude, this helps us to understand which of the smooth planes were in place before the other one. So the exterior plane were in place before the interior plane. And it's also very important because until this study, we thought that it was only filled by one high reflectance red plane, while here we see that it's filled by two different volcanic planes. And this is important for people that will do some modelization of magmatism of this area, that they have to consider different episodes of volcanism. So as I said before, I also wanted to understand the origin of the spectral properties and the spectral differences between the interior and exterior plane. So for that, I compared with compositional map that you can see here. And you can easily see that the high reflectance red plane within the Caloris basin are associated with the lower magnesium composition than the exterior plane of the Caloris basin. So I propose that with time, between the formation of the exterior plane and the interior plane, they have some modification of deep partial melting in the mantle that created lava with different composition, and that this difference in composition is at the origin of different spectral properties. And I will not develop here, but it agrees with different theory about magma evolution on Mercury, for example, or crystal thickness evolution on Mercury that validates this theory. However, so I just mentioned that locally we can associate spectral property with composition, but when we take a global scale, it's not necessarily always the case. For example, here you can see within the Caloris basin and the northern smooth plane, both here and here, you have the same high reflectance red plane spectral properties. However, when we check the composition, you can see that these two units are divided in three different geochemical terrain. So there must be something else than composition that will explain the spectral properties of the planet. And I propose to study the effect of space weathering. So to study the effect of space weathering, I performed some ion irradiation on Mercury terrestrial analog in the visible from the mid-infrared. So I used three terrestrial analogs that are a comatite, a basaltic comatite, and a boninite. So to be quick, there are three different high magnesium lava that we can easily find on Earth. And so I use a powder with a grain size below 36 micrometer, which is close to what we expect on Mercury. And I press the powder into pellets for some instrumental constraint. And here you can see the sample holders with the samples inside. Then I perform ion irradiation using helium at 20 keV, and we simulate more or less a maximum of 10 million years on Mercury of irradiation. And I perform reflectance spectroscopy again from the visible to the mid-infrared, so between 0.4 and 16 micrometers. Okay, and here is the result. So I put here only the comatite and not all the sample, but they all lead to the same conclusion. So here what you can see is, again, you have an absorption then that is not present on Mercury, but this is because of the composition of our sample that are just a bit higher in iron than what we expect on Mercury. This is why here we have probably we have this absorption dent. And when we increase the irradiation, so when we go to the yellow spectrum, we can see that there is no strong modification of this band around 1 micrometer. So it helps us to conclude that ion irradiation is not the main processes that play in reducing spectral signature on Mercury. And this agrees with the work done by Lavoretti et al. 2023. So to avoid this absorption then, so to stay comparable with Mercury, and be also comparable with messenger data, I only use the part before the absorption then. So I normalized the spectra at 0.5 micrometer. And here it highlights some spectral alteration with irradiation, what we can see between here, this color and yellow. And we can see a darkening of the spectra, which is a decrease of the albedo, a reddening, which is an increase of the slope toward longer wavelength, and also a flattening of the spectra until 110 to the 17 ion per centimeter square that you can see here. So this observation helped me to create three different spectral parameters: the reflectance at 450 nanometers, the slope between 410 and 500 nanometers, and the curvature, which will characterize this shape of the spectrum. And what we can see here, so here I put all the doses that we checked going to 510 to the 17 ion per centimeter square. And we see an exponential darkening with ion irradiation when we look at the reflectance in the top and left here. Then if we analyze the slope and the curvature, we can see that we have a decrease of the curvature or an increase of the slope only until a certain irradiation dose, which is around 110 to the 17 ion per centimeter square. And after this irradiation dose, we reach a putative plateau here, and we lose the flattening here, and we lose the reddening here. So I propose to focus only on the area where we have an evolution of the spectral properties until 110 to the 17 ion per centimeter square. And here what I did is that I normalized my spectra with the fresh spectra to test the intensity of space weathering on each sample. So what you can see is that for the darkening and the reddening, the basaltic komatiite is more sensitive than the komatiite than the boninite. However, for the flattening, it's a bit different. We have the komatiite here that is more sensitive to ion irradiation than the boninite here than the basaltic komatiite here. So here I will show you only one example, which is the effect of the iron content on the spectral alteration induced by space weathering. What you can see here is that when we decrease the iron content of our sample, we increase the spectral alteration, we increase the modification of the reflectance and on the slope. And this is very important because we expect a very low iron content on mercury. So on mercury, we expect even stronger modification than what is observed here. And this highlights that ion irradiation contributes to spectral heterogeneity on mercury. We easily understand that on the surface with different iron content, we will have different sensitivity and so different space weathering effects. To discuss a bit this result in the visible to near infrared, we observe a darkening and a reddening, at least until a certain irradiation dose. So first, this confirmed the well-known effect on silicates. And we propose that it can be due to submicroscopic iron particle and to the porosity induced by ion implantation on our sample. Then there is an area where we have a possible darkening without reddening of the surface. This is similar to what we have on mercury when we compare the low reflectance material with a very fresh crater. This is a trend that we observe darkening with no reddening. And it can be due to the formation of the submicroscopic iron particle called the Britt-Peters particle that are larger to the other one creating only darkening and reddening. About the curvature, so this flattening of the spectra induced by ion irradiation, my work is the first experimental confirmation that the flattening of the spectra is a reliable proxy of space weathering, at least for the youngest units on mercury. Then we perform additional measurement in the mid-infrared this time. So here you can see irradiation at 10 to the 17 ion per centimeter square. And I studied two different features, the Christiansen features, that is the minimum that you can see in the spectra, and the two different Ristral bands per spectra. And we observe for the Christiansen features, but also for the Ristral bands, a red shift of the features with irradiation. However, with the strongest dose that we perform, so 510 to the 17 ion per centimeter square, we see that the Ristral band are still red shifted, so toward longer wavelength. However, the Christiansen features is blue shifted this time. And to discuss this result, so the red shifts of the Ristral bands can be due to two different things, cumulative or not, the amorphization or a chemical alteration of the sample, for example, a preferential magnesium loss. Moreover, the shift is dependent on the composition of the sample, similar to in the visible to near infrared. I put you again the iron content here, and similar, when we decrease the iron content, we increase the shift of the Ristral bands. About the Christiansen features, so the shift depends on the composition. Again, so here I put the magnesium to show you the difference with the magnesium content of the shift. And so when it's red shifted until 110 to the 17 ion per centimeter square, I propose that it's due to like a dominance of olivine alteration, which is more sensitive than pyroxene. And it can be blue shifted after because it could be the dominance of the pyroxene with higher irradiation dose. So even in the mid-infrared, we confirm that ion irradiation can contribute to spectral heterogeneity on mercury. Okay, so if you remember, I show you that after a certain irradiation dose, we reach a putative saturation of our sample. However, here we simulate only around 10 million years on mercury. And when we study impact and effusive volcanism, for example, we are more here at 3.5 billion a year. until here, but it's very rare, like the maximum is around here. And here is what we simulate in the laboratory. So we easily understand that the spectral properties of old unit older than this Kuiperian unit can't be only explained by space weathering, like the composition has to be taken into account. So we highlight compositional heterogeneity necessarily. And this will help me to continue with my orbital data analysis, taking into account space weathering this time. So I studied different basins. So you remember calories? Then I studied Rachmaninoff, Rembrandt, Beethoven, and Tolstoy. They are all major impact basins on the surface of Mercury. So what I did is that I applied the spectral classification that I presented before to this basin, which is the Rembrandt basin. And you can see here, around the center of the basin, that we have more unclassified footprints, so more black footprint. We expected only red, like calories in the center of the basin. And I checked, and in the literature, there was this work from Samanzetto et al. 2020. So here it's a geostratigraphic map. So they combine morphological properties of the surface with spectral properties of the surface in the same map. And here they highlighted these yellow units, which is characterized by them as a younger volcanic infield of the basin, younger than the brown that you can see around. So this one would be younger than the other one. So I wanted to know if I could maybe sample this unclassified area to obtain the spectral properties of these youngest volcanic infields. And this is what I did. So same as before, I sampled the area, extracted the statistical analysis, built the framework. And here is a summary, including this new unit. So here you have the reflectance and the visible slope. Here you have the well-known low reflectance material, the low reflectance blue plane, and in red, the high reflectance red plane. Then I had this new unit that I called the young high reflectance red plane, which is here. And I also studied the intermediate plane that were not taken into account for now, that are here within the error bar of the low reflectance blue plane. So to make it more easy and distinguish them well on the surface, I just merge these two units in the following map that you're gonna see. And I had other spectral units just for comparison here to have an idea on the surface of Mercury. Here you have a fresh crater, and here you have Nater, which is a pyroclastic deposit from an explosive volcanism. And here are the results. So here you can see the new map with this young high reflectance red plane characterized here in orange. I will not go into much detail, but similar as Caloris, this crater here that you can see also here helped me to build the stratigraphy according to its ejecta and the disposition of the ejecta again. And below Rembrandt, I proposed a low reflectance material layer. So here you can see this mark. It's just because within Rembrandt, we don't have a very fresh crater like at Getz, where we clearly see the low reflectance in the center, being sure the layer is here. However, we can some deposit that help us. Here we can see low reflectance material here also. So I think that the layer exists below the basin, but it's not well excavated by a new impact. And then 3 different volcanic infield, the low reflectance blue plane like Caloris, that we can see the deposit here, the high reflectance red plane, we can see the deposit here, and the young high reflectance red plane that we find in the center. I also study other basin, again, the Caloris basin, because now that I improved the methodology, I wanted to check if I was still right in my numbers of infields of the basin. And I also analyzed Rachmaninoff, Beethoven, and Tolstoy. And here are the results. So just for Caloris, if you remember. So here you can see footprint in orange, and this area was mostly unclassified before. So for Caloris, the improvement of the methodology helped us to constrain even more the volcanic history of the basin with another volcanic infield, so 3 different volcanic infield. Same story for Beethoven here. However, for Rachmaninoff and Tolstoy, we don't see the presence of these young high reflectance red plane units. So I wanted to understand why. Why don't we have the same unit everywhere? Why is it not the same stratigraphy everywhere? So I checked the effect of the age. Does the age allow us to separate Tolstoy and Rachmaninoff from the others? No. Then I checked the effect of the composition. So no, again, you can see that they cover different composition. They have different background composition between Tolstoy and Rachmaninoff. So we cannot isolate them. I also checked the location, but you can see that one is in the northern hemisphere, the other one in the southern hemisphere, and Rembrandt has the young high reflectance red plane, Caloris too, but one is in a hot pole, one is in a cold pole. So the location do not have an impact on the presence of these volcanic layers. However, I checked the size. And with the size of the basin, we can see that Tolstoy and Rachmaninoff are both the smallest basin here. They are both the smallest. So I linked the size of the basin with the presence or not to the young high reflectance red plane. And there are two different hypotheses. So either impact basins that are bigger will go deeper in the surface and potentially reach a specific layer that will be at the origin of this young high reflectance red plane. Or it's just that when we have a bigger impact basin, we develop a stronger thermal anomaly in the surface that will generate more melt or a longer in time, more melt in time that will allow for differentiation of the magma. And in conclusion to this work, so I wanted to understand if by studying the spectral properties, we can have access to the mental property with these different volcanic fillings. And so we can conclude that there is no lateral heterogeneity in the mantle on Mercury, and we don't need this heterogeneity to explain the volcanic infield of major impact basin on Mercury. About the vertical heterogeneity, they are not necessary because of this thermal anomaly hypothesis, but I cannot confirm that there are no vertical heterogeneity at the origin of the spectral properties of the volcanic infills. Okay. So in conclusion, and for some perspective of my work, so if I have to summarize my work in one sentence, I would say that it helped to understand Mercury's geological evolution, taking into account the interior of the planet, the surface, and the environment interactions. And I want to highlight something, which is this close link between orbital spectroscopy and laboratory spectroscopy to show you how correlated they are and how we need both. For example, laboratory spectroscopy can help to better understand the orbital data that we have. Here we saw that probably iron irradiation is not at the origin of the lack of iron of absorption band on Mercury. Or we can see that nearly the entire surface may be saturated according to ion irradiation. Moreover, it helps to prepare future mission. For example, it helps to define some target or prepare future measurement, in my case, for example, MERTIS. However, we cannot do laboratory measurement if we don't have already data, so orbital data. For example, we need to choose a sample. So what's the composition of this sample? What's the grain size? Then what do we study in the laboratory? Do we study extreme high temperature or low temperature? And all of this, we have this information with the orbital spectroscopy. So doing both is important. It helps also to have this global view on the connection between the different parts of the planet. And of course, it's applicable to other airless bodies. So my work is in preparation to the ESA-CHACSAB Epicolombo mission. So here you have images of the last flyby we had a few weeks ago on Mercury. So the spacecraft, the mission is composed of two different spacecraft, and I will detail only for now two instruments. So the symbiosis instrument, which is a spectrometers and imagers, and it will provide global high resolution and infrared imaging of the surface in the visible to near infrared. And MERTIS, which is a radiometer and thermal infrared imaging spectrometer that will, for the first time using mid-infrared data, determine the mineralogical composition, but also allow us to obtain a thermal temperature map of the surface. So my work contributes to the future analysis of Baby Colombo with a minimum of 8 instruments that are concerned, including those 2. Moreover, I give some constraint for future analysis of the data with the amount of volcanic infill and so on. And I will allow the interpretation of the data taking into account the space weathering. So the continuity of my work. So here I show you this ongoing work. So you recognize probably the global classification. So before I was focused on very local area, like the impact basin. And here is the result of the global classification. So this is still an ongoing study because it's more complicated to interpret. We have to take into account all of processes that play an important role on the global scale, temperature, and so on, costs in the magnetosphere, and so on. And for the laboratory, so if I had to suggest, I would say that, of course, we need more laboratory measurements to test probably cumulative effects. Like here, I just did ion irradiation, but we can do ion irradiation plus heating, for example. Or to test the effect of the grain size. Here in my study, I focused only on 1 grain size. And of course, other ion and energy, because I remember that I test only helium at 20 keV, but there are plenty of other ion and energy to test. I have several ongoing collaborations that's starting a few years ago for some of them. I collaborate with Dr. Jack Wright on his objective to better understand the knobs on Mercury that are basically little mountain, conic shape of kilometer scale mountain around calories. And he asked me to perform the spectral analysis of this knob to see if we can correlate them with the hollows on Mercury. And this will help us to better understand, again, the calories basin and its area. I also work with Kaori Hirata and Professor Tomohiro Usui. So Kaori uses my work, so the spectral data that I presented around the calories basin, and she merged my spectral properties with compositional data and morphological data. And she could specify the magmagenesis below the calories basin even more than what I could do. And I also collaborate with Antonin Varnier back on the laboratory this time with ion irradiation on Phobos. And I also collaborate with Dr. Liam Morrissey and Sebastian Verkeek about a multi-scale understanding of surface exosphere connection within the NICI project. And to conclude, I would say that the PhD was way more than what I had the time to present today. I had the chance to teach during 3 years here at the Paris Observatory. Moreover, I did several outreach events related to women in science, for example, or also this amazing week that we had in Guyana to do some teaching and outreach. And finally, I want to thank my supervisor, Alain and Sebastian, but also my collaborators, so Jack, Kaori, Liam, Antonin, and especially Rosario and Kathleen, with who I performed the laboratory measurement IAS. Thank you.
Thank you very much. Yes, it works. Okay. So are you ready for the questions? Okay. So I will give the mic to the first reviewer, Pierre Vernazza.
Thank you very much. So I want to first congratulate you for the quality of your manuscript. It was very clear. I enjoyed reading it. Learned a lot of things. Catch up on the background of what has been done regarding Mercury in it and all the science that has been done. Was very clear and well done. So I will start with a naive question regarding the origin of smooth northern plains. So you showed us that most of the smooth plains are around the largest basins, and then we have this large structure in the north. What should we deduce? What is it solved? Is it understood?
Here. So unfortunately, no. So it's the only area on the surface that is, at least not for now, related to an impact. So there are different studies that focused to check if there was an impact below this smooth plain, but for now we don't know. It's the mystery.
Okay. Okay. Hopefully, Bepi Colombo solves it.
Yes.
Okay, I will go to the spectra, and maybe slide 15 makes it easy for the discussion. 15, yeah.
Sorry.
Okay. So you said that there's generally a lack of absorption feature, and that's the current consensus. Still, so the wavelength range covered by the spectra is okay, pretty extended. And I always wondered what the meaning is for those kind of inflections of changes of derivative that we can see in the spectra. If we look at the left, here it will be around 800. The slope changes a bit. Usually, for when bands are quite subtle, then this might be an indication of the beginning of a band. Of course, they're probably not completed the bands, but we see all these inflections. Couldn't it be hidden bands that will be revealed when the wavelength coverage is complete? I was been puzzled about this as general assertion that there are zero evidence of putative bands. Could you comment on that?
Yeah, so first I mentioned that there is no absorption band. It's still debated, of course, also between different instruments. So here are mask spectra. Within this, some study highlights some absorption bands. So here I mentioned this, but still it's debated and an ongoing question. About the 800 features, I don't know, but I don't know if it can be linked to this drop of reflectance in these features, which is probably an OMCT features. So it's probably the wings of an absorption band, which could be exactly, which could be in the UV. Yeah, it has been shown that this absorption band decrease when we go to older units because of this transformation of iron into nanophase iron that will decrease or stop the formation of this band. So I think it's probably influenced by the UV part of the spectra. Unfortunately, we will not have it with Bepi Colombo, but I don't know if I answered your question.
Yeah, okay, yeah. So if the same happens to something micron with the Bepi Colombo data, so if essentially the spectra remain mostly featureless, so then what? Just play with the reflectance slope, etc., as you did, and that would be really the benchmark for exploiting the data. So,
I mean, I don't know if we can see an absorption band, it could be very, very useful for the mineralogical composition, especially because now all the mineralogy that we suppose it's from XRS data, so from elemental composition data, but not from spectra. We don't really see the mineralogical composition. We deduce the composition according to geochemical models. So it's not very sure. So I really hope to see any absorption bands with Bepi Colombo. If not, yes, I guess we'll continue with reflectance, UV, the downturn, curvature, and so on. Maybe we will not have more information about the composition, but we can still work on the geological evolution of the planet.
Okay. So you selected a series of minerals for the space weathering experiments.
Yes.
Which is fine. Would you have any other minerals, key minerals in mind, and what would be your recommendation for the forthcoming experiments to continue this work? What could be, in your opinion, the key elements, minerals to target for experiments?
Yeah, so for effusive volcanism, if we focus on only terrestrial analog, I think those are pretty good. But if we want some synthetic analog, for example, this could be way better than my sample because we can simulate exact composition, especially in iron. So I briefly mentioned, and we saw it with this absorption band in the comatite, that I have some iron in my sample. And as the iron content on mercury is not fixed, I'm not sure how much higher I am, but a minimum of 2-3% higher than the maximum iron we think we have on mercury. So I would definitely go for lower iron sample, but then we have to move to synthetic sample. And if we want to study other specific area, like hollows, for example, we'll have to move to sulfide analogs. Yeah. Otherwise, also here are terrestrial anomalies, but we can go to some meteorite, for example, that would have properties close to Mercury.
Okay. Would you think it would be meaningful also to enrich samples with carbon or graphite, or to explain the low reflectance? Or
yeah, so here, yeah, if we want to simulate low reflectance material and the effect of ion irradiation on this sample, yes, we'll have definitely to introduce graphite. I'm thinking about graphite, yeah. But then I don't know if we will see a lot of alteration after space weathering experiment, because it will be already a bit flat because of the graphite content probably. But yes.
no, I'm saying that because carbonous chondrites, when you irradiate them, you see the opposite effect. So you bluish,
Yes.
and putatively it could be the effect of carbon. So that's why I'm saying whether graphite actually might confuse the trends.
Yeah, that's also why I mentioned cumulative effect. It's especially for that. It's to understand if we all go in the same direction for one sample, or no, if they have like one increase, another decrease, and so understand which one dominates to understand the property. Yeah.
Okay. And maybe we'll end up with a question regarding the different compositions between the impact basins. So it's pretty convincing that the infills in the basins came after the surroundings. So how about other small craters across the surface? I mean, you focus on 4 or 5. Yeah. Does the trend repeat or all the time? Have you had the time to look a bit at that, or?
So I didn't include more impact basins, like I hope to do it in the future. The only point is I have to include basin big enough to have been filled by the volcanic layers, but there are some others. So yeah, to validate, I could test additional basin, but I also have to have enough footprint, and it has to be like well preserved, or at least a minimum to be able to perform the classification. So those are best candidate also because they are a bit already studied in the literature. So it helps to understand if some people already did some topographic analysis or some morphological analysis, then I can be sure I'm not biased by a fault or something in my results. So that's also what motivated me to choose this one.
Okay. And so would you consider the surroundings of Caloris and other basins as the best remnant of the primary magma, or?
So this low reflectance blue plane can characterize smooth plains or intercrater plains. So when it's smooth plane, like around Caloris, I would not consider it's the primary volcanic unit because it's smooth. So I would say that it's younger. So I would say no. Then when it's associated to intercrater plane, probably it can be related to the first magmatism on the planet.
Okay, I will thank you very much.
Thank you.
Thank you. So I give the mic now to the second reviewer, Antti Pettila.
Thank you. Okay, very nice work, very nice. This lecture here is actually, the lecture already answered some of my questions, so it was good, well thought. First, I can start with very general question. So you had in your thesis, you had a very nice introduction to these 3 missions. So the Mariner 10 messenger, and then now the upcoming Pepi-Colombo mission. Can you somehow very briefly say how are these, I mean, how are these different on the type and amount of information they give on Mercury? So sort of compare these.
Yes. I will just go back to the slide. Okay. So with Mariner 10, a lot of things. First, we can image only half of the planet. So everything we discover, we cannot be sure it's we cannot be sure we can extend it to the entire planet. I'm thinking also about tectonic features, which was a big debate at this moment. Moreover, we do not have elemental composition with Mariner 10 data. So those 2 points were very motivating for the messenger data. Also between the 2 missions, so Mariner 10 also discovered some elements in the exosphere, for example, and it also motivated the ground-based observation in between the 2. And then we arrived to messenger. So here, after 1 or 2 flyby, we had the entire surface of the planet, which was very a big step. And we also have this composition of the surface. So even if it's very limited, but it revolutionized our understanding. And we could see, for example, some features that we call ghost crater that are ancient crater covered by smooth plain. And this was one observation allowing us to say that some of part of the surface was volcanic. So this was also a big step reached by messenger. Then I'm thinking about spectral data. For example, on messenger, we have MASC, which is the point spectrometers. And with BepiColombo, we will have the spatial also part of the spectral measurement that will improve the data. And of course, the MERTIS observation that it will be for the first time of remote sensing observation in the mid-infrared. So this will be also a major contribution of BepiColombo to help us with the mineralogical composition of the surface and the physical properties of the surface also.
Okay, thanks you. Then about the correlation between the elemental ratio maps that we had from messenger, and then the from the X-ray spectrometer observations, and then the spectral units. So not the geochemical units, but then the spectral units that you have, for example, in your slide 45. I know it's difficult, but is there can you find any global correlation between some elements on the elemental map and the spectral behavior?
So I can show you something. Here, that is in my paper from 2023. I think it can help answer your question. For example, so spectra, no, but spectral analysis, probably. Here you can see the white dots that are low reflectance material. And we can see that it's heterogeneous between the east and west side of the basin. And it seems to be directly linked to the composition. And also some previous study show that. I'm thinking about Nittler et al. 2020. They also saw this close link between low reflectance material and aluminum content. You can see. I don't see well, but you can see the composition. And so the footprint will be associated with lower aluminum content. So this, for example, is a link that can be done with the spectral analysis, not directly the spectra, but the spectral analysis.
Okay, interesting. Thank you. Then continue with the optical properties. So this is intriguing question, I guess, in general, that what makes mercury so dark? So it is more magnesium rich than iron rich, but is there still enough iron for this extensive space weathering? And then about carbon. So C-type asteroids, they are very dark, they have flat spectra. Is there carbon in the upper surface of the Mercury? Is there some link between C-type asteroids? So what is the darkening agent in Mercury?
So about the carbon, it plays a role in the darkening of Mercury, so especially this graphite within the low reflectance material. And also because with the carbon, we can create this kind of same nanophase particle that will also participate in the darkening of the surface. So this would be, again, related to the space weathering. And then about the iron content, so some studies show that only even with a very, very low iron content, it's 0.02, we can create the particle that will modify the albedo of the spectra. So even if we have 1% or even 0.5%, it could happen on Mercury. And actually, they showed that, so they simulated and they obtained 3.5% of nanoparticle iron on Mercury, and 3% of them could be the big one, the Brid-Peters particles. So it's a process that can or could work on Mercury.
Okay. Maybe a slight follow-up to this. So you say in your thesis, or you cite sources that say that the lack of this 1 micron band in absorption is an evidence of low iron oxide content. I'm maybe wondering, are there any other evidence to support that? Because we know that if we have extreme space weathering, it can mask quite well. Maybe this was something that you also asked. It can mask quite well all absorption bands. So are there any other evidence that there should be low iron oxide content?
No, I think, so between those hypotheses here, I am not, and I'm not sure we can choose one or another to explain the lack of absorption then. Personally, I think that it's more cumulative effect of different things, but I'm not sure we have an evidence that for sure the lack of band is related to the iron content, because even some study showed until 8% of iron on Mercury. So this, for example, we would expect some bands if the instrument that we use are resolved enough to see the bands. And it's also the problem with mask, actually, with mask and MDIS. So.
Okay, thank you. Then a question about your spectral classification into units. You have there these confidence intervals. They are ranges where this parameter should be, I guess, in the ±1 sigma range, yeah, or something like that. And then you assign also these points giving sort of weight to different parameters, yes, with how you see them affecting. Now this is just a small criticism, not large. This whole method seems a bit ad hoc. It seems like you have these parameters, you look at them, you wonder what can I do with them, and then you invent this kind of procedure. Could you see some other methods, maybe more matured in statistics, to sort of reach the similar conclusions? Because I think the conclusions are right. I think the results are correct. No problem with that. But the method is maybe just a little bit, as I said, ad hoc.
Yeah. So there are other studies that did more or less the same with unsupervised classification of mask spectra, for example. But what is, let's say, powerful with my method is that you can play with it according to the area that you're looking at. So this quality parameter that I created, what is interesting is that you can play with it and be more strict or less strict, and it helps us to work with mask, because we don't have this spatial coverage that is like on the entire planet. So you have to use a method where you can adapt it to your targets. So this, for example, it will be more difficult with another methodology, for example. But yes, also like Mario D'Amore, he did it with unsupervised classification, and we have more or less exactly the same map.
Okay, good. Then about the simulations, laboratory simulations. So you simulate space weathering with ion radiation. You do not simulate micrometeorite bombardment with these laser shoots. Are there some features in the space weathering process that you think you might miss because of that? And maybe further, do you think there is anything you miss by having these helium ions and not other ions?
So about absorption bands, as I worked out of the absorption band, no. However, using laser, I guess I would have more alteration, like more important spectral alteration with the laser or with EV ion, for example. So I don't know if we miss features, but probably the intensity would be different. Or the area when I see only a very weak alteration, maybe we miss a very strong alteration in just when we accumulate or when we use micrometeorite bombardment, for example.
Okay. The space weathering effect on your laboratory samples, this comatite, basaltic, comatite, and boninite, I would say they are not very strong in the visual infrared. For example, I have seen a lot stronger effects, this darkening, slope change, band flattening in olivine, for example. Yeah. So do you think, is this a feature of your samples, or if you would have a different kind of experiment, for example, simulating also micrometeorite bombardment, could you see more? Could you make them even more darker and see even more effects?
I think yes. I think, but if they all go in the same direction, like if they all darken the surface, I guess it would have been darker with a laser, for example, or accumulating laser plus space weathering. I'm not sure, but I think it's what I would expect.
Yeah. Okay, good. I have just one final, again, a bit general question. About the Bepi-Colombo observations, do you think your work can somehow influence when we are planning the observations? Do you think that you can have some input on what we should observe?
So you mean how my work could help in the future?
Yes.
So I can show you something. This figure, which is also in my paper. And so it's kind of figure that we developed also with Kathleen and Rosario and we think we could put the Mertis data on it because, for example, the steepness of the vector that you can see here will give information about the space weathering and the amount of space weathering, so simulated time. So, for example, this kind of figure and putting Mertis data inside could help to distinguish different ages of surface, for example. But I also have to say that for the shift that I show, not all of the shift would be detected by Bepi-Colombo. Some of them are too small, for example, for Mertis to be detected. But we know that if we expect one spectral features around with this wavelength and we don't see it, or we see it like in another wavelength, it can be due to space weathering. So I think my work has to be kept in mind when we analyze the data to not miss some information, for example.
Okay, I thank you for all your answers to my questions.
Thank you.
Thank you very much. Now we are switching to the examiner, and I'm asking Mrs. Kerry Donaldson Hannah, do you hear us?
I do. I can hear you.
Okay, so do you want to? Yes, we hear you. Do you want to make some comments and ask questions, please?
Sure. Congratulations, Emma, on putting together such a fantastic thesis. I really enjoyed reading through the combination of remote sensing data as well as laboratory studies, in particular the mid-infrared spectroscopy. I did want to start with maybe some general questions. The first is, so you see a general trend of only identifying the young high reflectance red plains in the largest basins. Could this be a spatial resolution bias? Is it possible that there could be some of these similar materials in the smaller basins, but the mass data just can't resolve them?
I don't know. So I also think like your question make me think about something that it's complicated because the smooth plane, we have to be sure it's volcanic in origin if I want to use them to understand volcanism on the planet. And I think this would be maybe even trickier with the small basin, with this problematic of differences with impact melt, you know? So maybe we miss some smooth plane in some small crater. So I think in any case, for sure, we will have more information about the morphological point of view. So also about the volcanic origin or no of other planes. But yeah, I guess it's possible that we miss some.
Could you then maybe speak to the spatial resolution differences of the masks instrument and what we're expecting with Murtis and Symbiosis, and how Bepi Colombo may or may not do a better job at resolving volcanic units and addressing some of the questions that you left to be answered in your thesis?
Yeah. You sorry, I didn't hear well. You mentioned spectral or spatial?
Spatial resolution.
Okay. Yes, so for sure. So with I mentioned with the symbiosis data, we will have with this spatial resolution that we don't have with messenger, with the mask data. So I mean, for sure, we will have more information. Also, the footprints, like the size of the footprints, I'm thinking about this, especially in the southern hemisphere. So my analyses are very limited in the southern hemisphere. So even if I filter the footprint below 65 kilometers square, some footprint overlap different unit, you know. So I think I missed some information here that we will certainly have with BP Colombo. With a better spatial resolution, we could be sure to target one specific unit and not be in between two different specific units.
I believe it was Pierre that asked a question about, is there a possibility that with Bepi Colombo, you might just have flat spectra and that you'll just be stuck looking at slope and curvature? Do you expect that to be true for Murtis and Symbiosis, or are you expecting that maybe you might get different data out of different wavelength regimes that would give you some compositional understanding of the surface?
So from ground-based observation that we have now in the mid-infrared, I would say that I don't expect a flat spectra in the mid-infrared. I expect some features. And even if we don't have even if we have a low iron content, I expect the features in the mid-infrared. So no, I don't expect a flat spectra. I also tried to compare my data at a certain point with the mid-infrared data we have from ground-based, but it was a bit hard to compare it. So I didn't focus on this too much, but definitely I think we will have features in the mid-infrared.
I was hoping, so transitioning to the lab measurements that you made, I was hoping that you could talk through the method that you used in identifying the Christensen feature position. Like, could you please talk through that?
So I identified the Christensen features by the minimum for each spectra. So this is how I proceed to have it. And so just to complete for the Australian bands, I also did it with the maximum of the spectra. And then the other one, I did it manually, like visually. But for the Christensen features, it was the minimum of the spectra. And even if for some reason, sometimes we feel in the plot that my vertical line are not in the minimum, they are.
So then you are taking the minimum of the lab measurement. So what is the spectral spacing or the spectral sampling of the measurements? And do you think that your results would be the same if you perhaps fit a polynomial to this region of the spectrum at a higher sampling, and then identify the minimum in that fit polynomial?
Yes, so the collecting spot is 3 to 4 millimeters. So it's enough to be heterogeneous when we check the surface. And here, for each spectra that you see in the mid-infrared, it's an average value of several spectra. Oh, so I don't remember, but from the top of my head, like 5 or more spectra. And for each spectra, I took it at different area on the sample. So I would expect the same, maybe not in intensity, but for the spectral features, yeah, I would expect the same in the entire sample.
Yeah, so I guess what I was asking is, do you, in finding the minimum where you identify the Christensen feature, you're currently doing that in your lab data, like at the resolution of your laboratory data, which isn't necessarily where a feature might occur based on chemistry or composition of the rock. And so I guess what I was asking maybe is, what is the error in your approach of finding the CF doing that rather than fitting a polynomial to that spectral feature and identifying the minimum in that polynomial?
Okay, now I understand, but I don't know. I didn't check. I didn't try with the polynomial, so I don't know. I think that in any case, the trend would be the same, but the exact position, I don't know. I'm sorry.
Yeah, and out of curiosity, how heterogeneous or how different were the spectra? If you were to plot the standard deviation of the measurements onto your average spectra here, how big would those uncertainty bars or standard deviation bars be? Like, are they smaller than the width of your line? Would they be double the width of your line? What do you think?
So here are normalized spectra. And I remember when I plotted the unnormalized spectra, we have quite differences, especially in the reflectance, like not necessarily in the shape, but in the reflectance. Can you repeat the end?
Yeah, I was curious if you added, since these are average spectra, if you added the standard deviation of the average onto your spectra here, how would they relate to the thickness of your lines here, just to give a sense of the variation that you saw in your measurements?
Yeah, I don't exactly know. But certainly like visible for sure. Like if we take only one spectra and another, for sure, it will be easily visible, maybe twice the thickness.
Okay. That makes sense since you were measuring across multiple parts of the sample. And then would that change your CF positions that you identified? Or was the CF position always the same?
For the position, I don't think it will change a lot if we consider that in any case, the sample is more or less homogeneous and that and comparable. So I don't think the exact position would change a lot, but again, I didn't measure them separately before this average, so I don't know.
Okay. And then I have one final kind of fun question, which is, obviously we don't have sample return missions planned to Mercury, in the near term, but if you wanted to really go after some of the space weathering questions or some of the volcanic questions that you have identified in your thesis, where would you think of returning samples from to analyze in Earth labs?
So if I think about space weathering, I would say something fresh to try to be maybe not completely saturated, or see in the fresh sample what do we already have. Do we have this nanophase formation, or yeah? And then if I'm thinking about the volcanic side and the calories part, I would like to sample close to ADGET or like within calories, but the objectives are different. But if I had a target for an impactor, I think within a smooth plane to check my hypothesis about the different layer.
Great, thank you. That's all I have.
Thank you.
Thank you very much. Okay. Now I will ask Anna Mililo if you have a question.
Thank you, Emma, because I am not so expert in this space weathering, so I learned a lot from your thesis. So thank you. I will have some questions that probably are a little bit strange because I am not in the field. So I hope that you can at least answer a little bit. Okay, now the first thing is about the experiment. So you are simulating the space weather with this sample that are a kind of mixture of different mineralogies. My question is the space weather effect for different poor mineralogy just a cumulative process? For example, if you have 50% of olivine and 50% of pyroxene, do you have the global effect is just the sum of those, or is there is also some interconnection between different mineralogy, the effect? So it's just a sum of, so for example, you said that for olivine you shift red and for pyroxene you shift blue. Is just an addition or is something different?
So I don't think it's an addition, but so for this example that you gave about it's olivine or it's pyroxene, it's here. So I proposed this hypothesis because, so first in the sample, everything is mixed. Like we don't have the olivine on one side and the pyroxene. And here I proposed that because some specific space weathering experiment on olivine and on pyroxene show that. They show that the olivine was red shifted and the pyroxene blue shifted. And it correlates with my sample. So the one that have the most important olivine content, I mean, I related this to the content. So when we had more, for example, in the mid-infrared, when we had more olivine, I expected more shift. And this is why, for example, here, I propose also in the paper that for the Caminiti, we see that the maximum is shifted. It's the first absorption, the first Australian bands, and then it goes to the second one. Probably this can be due because this sample was the richer in olivine. So yeah, so no, I don't think it's cumulative. It's more taking into account who will be more impacted than another and correlate it with the amount of the mineral that I have in my sample. I don't know if it's
so. Yeah, no. So if could be better, for example, to make the experiment for poor olivine and poor pyroxene, for example, to better understand, and then you, for example, know that a unit in mercury has a composition of both, and you can just mix the effect in the lab.
Yeah, so experiment on minerals have been done several times for silicate, especially for olivine and pyroxene, for asteroids, the moon, Mercury. So this was already done. What I wanted here is sample that would be closer to a real rock that we could have. But I could do that because I already knew the effect on olivine and pyroxene. Of course, if we have a rock with no idea of the separate effect, it will be harder to interpret the results. And yeah, the ideal sample would be to have different minerals, measure them, crush them, mix them with the exact percentage that we want, and then we have a perfect synthetic sample for our sample.
Thank you. The other questions, again for space weathering, is about your impacting ions, as also Antti said. You use the helium plus at the 20 kV. Okay, the solar wind is a little bit lower and is hydrogen, but we have a lot of heavy ions also around Mercury that are accelerated. So these energy are not so strange, I think. But my question is, which is the effect, again, in the space weathering effect, if you have lower energy or different masses?
So different things. So first, with the higher energy, we simulate a longer period. So this is 1 point for the laboratory. Then so the effect on the surface will depend on the energy, of course, on the material and on the type of ion. So we can have different effect, but it can be in intensity. As I mentioned with the laser thing, probably with EV ion, we can have, have a study in mind where with the argon, they have more modification that with helium, for example. So this is the kind of difference that we can have.
For example, could be that implantation change in.
Yeah, so the first, the depth reached will change. We can go like deeper or less deep in the sample when we irradiate, and this with the measurement has to be taken into account, because we can, if we irradiate only a very, very thin part, when we'll do the measurement will be after the irradiated layer. So we will see less modification than if we go directly within this irradiated layer. So the difference of the condition that we have in the lab, it will, yeah, not have the same effect on the sample.
Okay, thank you. So, the other question is, again, also maybe Antti said something about the microparticle of iron. I understand that you answer already that we cannot directly understand if there is iron from this measurement, which is at least the percent, the composition. But is still true also in the, for example, X-ray in atomic band, you know, if it's possible to check if there is iron in other.
So the iron content we have, I think it comes from XRS, also from the X-ray. But also I have to mention that the map we have for the iron content, it's not global. We have, so as with the X-ray, we have this dependence on the sun and the activity of the sun. We have global map for magnesium, aluminum, and silicon, but not for other elements. So I think it also restricts a lot our interpretation. We have some area where we don't have the iron content on the surface. But otherwise, yeah, the iron content we have come from more elemental composition that only checking the spectra and saying that we don't see the band, so we don't have iron.
Okay, then I have another question about the general Bepi-Colombo measurement. For Serena, for example, we will have, you already mentioned in the thesis, that we have the ion sensor that will map the precipitating particle, and we will have Elena that will map the impact onto the surface. So what I think could be done together with the MERTIS and other measurement is, for example, a kind of statistical analysis of our data, our mapping to compare for different unit, for example, no?
Yeah.
But do you have something else, or can you suggest some specific measurement that could be useful?
So from Serena, for example. So first, the MIPA analysis of the ion and the energy. So this will help for the lab because we will have more constraint and we will know, for example, okay, we simulate this energy, but for mercury, I don't know, only this percentage arrive with this energy. So it's okay, we can do the analogy, but maybe we have to be careful. So this is what I missed. So here I worked with the proton precipitation, but this exact map with ions and other precipitation is exactly what we would need to compare with the surface and to interpret the lab data. So this kind of geographical representation would be very interesting.
But for example, do you think that some specific region, apart from the global map, do you think that there are some specific unit that could be interesting for a statistical study that could be compared? I don't know.
So if I think with the properties of mercury, hot pole, cusps, and all of this, calories is in the middle of a hot pole. So probably could be a good target to see the effect on the hot pole. And for example, what would help me is if I had the data on Rembrandt and calories, I would be directly able to link it with the hot or cold pole. So targets like that are big target, would be very useful to compare the area and also be sure I'm not biased by this component of the exosphere and all the precipitation and exosphere formation and so on.
The final question, or at least is a kind of really open question or comment. You showed the very last slides about the global mapping, the new work. Yeah. I see that there is a very clear difference between longitude, hot and cold pole, maybe. Could you explain? Could you comment that?
So I'm smiling because it's exactly the topic we were discussing with Sebastian. So what we try to do is first try to have this map, but only focus on the smooth plane. And it's changed a lot because we have less this repartition. So first this changed, and it's more relevant because I defined my unit on smooth plane, so of specific ages. So it would be more relevant to focus on exactly on the smooth planes. And I cannot really spoil everything, but I'm not sure there is a real link with the temperature and our spectral property, even if when we look at the map, we would say one is hot, one is cold, one is hot, one is cold. It's not necessarily what influences our data.
Okay. I can have also an idea. There is also a difference in micrometeoroid precipitation that is more or less related to, it's not the same cause, but the hot pole and cold pole correspond also to region where micrometeoroid impact more or less.
Okay.
For the resonance. So could be that the meteoroid renew the surface.
Yeah, definitely. We have to check this. We didn't check for now, but yes, definitely. Okay. Thank you.
Thank you. That's all.
Thank you very much. Now I ask François Poulet.
Thank you. So I concur with all the previous remarks about the quality of your manuscript. It's really impressive. I think the background, all the first part is really nicely presented. All the background in terms of science, and it covers both. It presents very well the background for your work, which is why it's very nice. I appreciate a lot the reading of your manuscript. Also, I think you selected also a nice figure, which represent very well the current knowledge of the science of Mercury, on the understanding of composition of this planet. I think I don't have too many questions because most of the previous colleagues have already asked many of my questions. You also, during your presentation, answer some of my questions. So it's very nice to answer to the expectation of the jury. So it's always nice to see that. I still have some question. Actually, you mentioned in your manuscript, page 39, that the collocation between the effusive volcanic smooth plane and the impact structure is consistent with the contraction. Do you think this is something which is well constrained? And with your work, do you think that you can provide additional insight about that?
So it's constrained with the impact basin because of this contraction. But the first mechanism of all of this is the cooling of the planets. Yeah. So first is the cooling that will decrease the magma production within the planet. And then this contraction will distribute the magma within the impact. Now, I don't know. It's also, so with this global map, to try to answer this and see if I can learn more, I think I have to include the northern smooth plain in my analysis and learn more about this, because I can classify them as some specific volcanic units that are within the basin, but they are not. So maybe if we can understand why do we find this young high reflectance red plain, for example, also in the northern smooth plain, we can have more idea about if first the origin of the plain and this link with the basin, if it's really the basin that stopped the magmatism on Mercury or no.
And actually, one of your answers about the methodology was a little bit puzzling for me, because by staying on this, by looking at this map, because you mentioned in one of your answers that the methodology what you implemented should be focused on a restricted region, not for the global study. Yeah. And so this is why I'm surprised to see this kind of map, even if it's a very nice map. So could you explain a little bit more why you go further?
Yeah, so this is, I really hope to have a global map, yeah. But so because also of the methodology, it's very hard to understand the distribution of the entire map. Also with the methodology. So again, we discussed this just yesterday about how we could improve the methodology to better understand, especially for here we don't really see, but there are a lot of unclassified, like these black footprints that are unclassified. And I think I need to work on the methodology to reduce this number of unclassified, because they are mostly in between the units. So I think there is something to improve in the separation of the unit to include more footprints, and to know which part of this map is linked to the methodology and which part is real or related to the spectral property. So some work to do in the methodology and interpretation.
Okay, so related to this uncertainty, I'm a little bit surprised that you did not show any spectra of the different units. Why did you not show anything?
So I didn't show the spectra because I didn't really work on specific spectra. Like, for example, I never plotted all of the spectra because I'm more doing something on a big scale, but I have somewhere here. So here are the spectra of the different units. Okay. So I have I did in my analysis kind of the same figure with also a Mercury average to be sure. I validated the N members sampling and all of this, but from the spectra, one by one, I would not learn more with my methodology, as it's like global statistical analysis.
Okay, but did you check that I will say maybe the median or the average spectrum from yes, they look similar to?
Yeah, I plot okay. I did the same. Like I didn't publish it at the end. I didn't put it in. No, it's not in the paper. But yeah, I did it also with Mercury to be sure I was either below or not there.
Because when if you show again the map of around calories. it looks like that the white spots are like looks like noise. Yes, exactly. Yes.
Yes.
For instance, okay, when you show the global map, it does not look like noise at all.
Yeah.
But when we see that, okay, for I think for the crater which is within inside the crater floor of the basin floor, there is no doubt about that because you have very nice geological correlation. So this is clearly supports this different composition. But for the other points, okay, you see like bands. So
Yeah.
are you sure? Yeah, okay. So you check the spectrum and the spectra, and you are quite confident that it's real. Yeah.
Yeah, so I'm happy about this question because it was a huge part of my first paper. So I checked for example, also other thing like the time and the day of these footprints to see if they were all taken in the same day. For example, we could just say, okay, maybe something happened in the instrument, but it's not the case. And as you mentioned, it worked very well for some area. And then we have this band. So I remember that I checked everything, like all it was possible to check, I checked. And also what comforted me is when I noticed this correlation with the composition with aluminium. So I discussed it also briefly with Larry Nittler, who did the compositional map. And like we cannot say that it doesn't exist. Like it correlates pretty well, taking into account the uncertainty both of the spectra and the XRS data. So at the end, I was confident that it's real, but still.
But maybe to reinforce your confidence, it will be nice to plot both the spectral parameters on the chemical composition.
Okay.
In the same plot, just to see if you have some correlation or not. It could help to to discriminate the different units. Yeah. What is a spatial resolution? Because I had a similar question than previously. What is the spatial resolution of this instrument here, for instance, in calories, typically?
For the footprint?
Yeah, the footprint, yes.
So I filtered them out of 65 kilometers square.
65, okay.
So they are below.
Okay.
They are usually way lower, but I had to put like a limit to avoid, I didn't want big, so I checked the footprint. And what I didn't want was one that was in the middle of the two units, because this bias, the statistical analysis, we don't, like the spectral property are mixed. It's neither one or the other. So this is how I filtered the data. But otherwise they are way lower.
Lower 165 kilometers.
Yeah. Okay. Yeah, it's the max.
So it's huge, you know, because with symbiosis, we will reach similar map at 500 meters, something like that. So I think based on the previous planetary missions on other objects, as soon as you start to increase the spatial resolution, you revolutionize actually the knowledge of the composition. So I think we are going to have a huge surprise with symbiosis. So now I understand better the limit of the data, and I think you do your best based on this data set, because there is not a great spatial resolution, and also the signal to noise is not great as well. So yeah, okay, congratulations for that. I just have a last point. It's about the recent. You show that very nice picture of the fourth flyby of Mercury. On what are the main outcome of this flyby? I know that MPO did not operate, but from the other instrument, do you have any interesting thing to say? Because I did not really follow it. This is just for me as well.
So I tried to follow the last SWT, but it was only a few days ago, so I was a bit working on the presentation. But I noticed, but first, I mean, Anna can say more, but about this ion precipitation and the energy, I was happy to see that they measured energy close to the one I used in the lab. That comforts about the analogy I'm doing in the lab and what they measured with Serena. So this, for example, for me was a good point. Then about mineralogy and anything related to surface, nothing, even like the altimeter didn't operate at the end. So I think it's mostly magnetosphere and exosphere data that we got, not except of Serena and the precipitation. I'm not sure it can be really related to my work for now, what they found.
Thank you very much for your answer.
Thank you.
Okay, thank you. I have to apologize because I have forgot to introduce the invited member of the jury, Kathleen Lance. So I would like to know if Kathleen wants to say a few words or ask questions.
Hi, Marie-Christine. Yes, thank you. Can you hear me?
Yes, we hear you.
Okay, I'm sorry, my voice is not very loud. Sorry for that. And again, Emma, I'm really, really, really sorry and sad I can't be here with you today. I just wanted to say a few words. Obviously, I won't ask any questions because I did work with you. But I really wanted to say that well done, because I know how challenging it can be to be working both with people doing remote sensing data space mission and then talk to people doing the laboratory experiments. You did it well, especially in the context that at some point, Rosario and I were not here for you. We kind of abandoned you, but it was not because we didn't enjoy working with you. Far from that. It was really, really great to have you. And I also want to congratulate you because I've not been here for months, and yet you managed to go with your paper, the laboratory paper. You did a lot of work. You hard worked on this alone. And for that, I want to say to the jury that Emma really did a great job trying to do most of things without having any supervisor efficient at this time. I'm really also happy because in the end, you seem not turning too mad with the lab, because you're going to do a few months of postdoc doing again some laboratory experiments. So it is great. Maybe my job giving you this introduction to the lab field was kind of okay because you still want to work with that. And again, I want to thank you because even though you were the student, thanks to you, I really learned stuff on Mercury because I was really brand new researcher on Mercury when we started working together. And so thank you very much for all the discussions we had together. And congratulations for this PhD. Well done, Emma.
Thank you.
Thank you, Kathleen.
And stay alive, Kathleen.
I'm trying.
So now it's time for the supervisor. I let you organize.
Okay, Emma. So I excuse myself to Auntie and Anna, but I will do it in French now so that your family can also hear a bit of those words. That's important. We've passed through that as well ourselves, so we do that. Donc on a donc très bien, hein. C'était très bien. Moi je me suis bien éclaté encore une fois. Ça fait 3 ans qu'on a passé ensemble, encore un peu plus pour Alain, qui a eu l'occasion de te co-encadrer aussi pendant ton stage. Je pense aussi à Océane, qui doit probablement être en ligne à t'écouter, qui doit être assez contente et assez fière d'où tu es allé. Il y a des choses intéressantes que j'ai bien aimées moi dans ta thèse, parce que bon, on est tous passés nous dans le comité en général par une thèse aussi. Moi j'ai retrouvé quelques éléments de ma thèse dans la tienne des fois. Je voudrais en citer un ou deux parce que je trouve ça assez intéressant de comment tu as avancé pendant ta thèse. Le sujet qu'on a mis en place avec Alain n'était pas facile. Je ne vais pas répéter ce qu'a dit Kathleen, mais à la fois faire de l'orbital et du laboratoire, moi-même, je n'aurais pas osé le faire. Donc, de le donner à quelqu'un d'autre, c'était encore plus compliqué, mais tu l'as bien réussi. C'est quelque chose de très bien. On a réussi tous ensemble à avancer là-dessus. Au début de ta thèse, tu as commencé, il y a 2 choses qui m'avaient marqué très vite et aujourd'hui, elles sont, je les aime beaucoup. J'étais venu quelques mois, parce que bon, on ne s'est pas vu tout le temps, mais j'étais venu ici quelques mois après. On travaillait sur Caloris. Et Emma qui me dit, ouais, mais bon, Sébastien, ils racontent tous des choses différentes partout. Je comprends rien, moi. Je dis, bah oui, bah, c'est le boulot. Et ensuite, Emma qui me dit, non, mais moi, en Python, je code pas, hein, c'est pas la peine. Hein, j'ai pas envie, hein, je fais autre chose. Bon, ben, regarde où tu en es aujourd'hui. C'est toi qui dis aux autres ce qu'il faut qu'ils fassent et les interprétations. Et c'est toi qui fais tes propres codes en Python et en quoi que ce soit que tu as envie de faire plus tard. Donc, félicitations pour tout ça. C'est quand même quelque chose de très bien. Kathleen l'a bien mis en avant. Tu as réussi, je voudrais insister là-dessus parce que ce n'est pas mon expertise en plus principale, mais la partie laboratoire était très bien. Tu as réussi à réunir Alain, Rosario, myself et Kathleen ensemble pour faire ce travail. On a publié un papier tous ensemble. Ça n'arrivera pas tous les week-ends, je crois qu'on sera tous les 4 sur un papier. Donc, bravo là-dessus. Tu as quand même été, pour une grande partie en tout cas de ce que j'ai vu, tu as fait le lead sur ce projet de laboratoire. On savait ce qu'on voulait faire dans une idée, mais après, c'est toi qui es allé faire toute la démarche, tu as choisi tes échantillons, tu as choisi tes mesures, tu as pris le meilleur de chacun de nous quatre et tu as enlevé le plus mauvais de chacun de nous quatre aussi en disant ça, je veux pas de toi, ça, je veux pas de toi. Donc, tu as réussi à bien prendre tout ce que tu avais besoin pour avancer. Tu l'as fait très bien. Il y a un point qui est très important, c'est dans la slide juste après. Tiens, d'ailleurs, ça tombe bien. Ouais, je crois bien. Non, ouais, celle-ci, là. Où je veux insister là-dessus pour le reste du comité. Pour moi, c'est assez important, c'est-à-dire que ce carré vert en bas de ta collaboration avec ses collègues au Canada et en France, que ce soit Alain ou moi, on n'a absolument rien à voir là-dedans. On l'a même appris après, et ce qui est très bien en soi. Mais de réussir à faire ce genre de choses pendant une thèse, c'est très rare. Je ne sais pas si d'autres l'ont réussi, on peut en reparler, mais c'est très bien. Tu as monté tes propres collaborations toi-même à l'extérieur pendant ta thèse. Et ça, c'est quelque chose de très, très bon que tu as réussi à faire. Donc, bravo pour ça. J'ai plein d'autres questions, j'ai plein d'autres remarques, tu me connais, hein, mais ce n'est pas mon rôle aujourd'hui. Donc, on en parlera plus tard ou pas. On verra ça. Donc, bon courage pour la suite et je laisse Alain terminer.
Well, I will switch to French because it will be interesting also for the family to understand. Ok, Emma, donc d'abord, félicitations pour ce beau travail. Mais effectivement, je te connais depuis 4 ans, depuis même les cours de master. Donc déjà, une thèse, c'est quelque chose qui est un long projet, hein, 3 ans. Il y a des hauts et dans ton cas, il n'y a pas de bas, mais des moins hauts, mais ça c'est normal. Et tu as su les gérer merveilleusement. Tu as su, comme je ne vais pas répéter tout ce que Sébastien a dit, mais tu as su effectivement faire travailler plusieurs personnes ensemble. C'est vrai que nous sommes des directeurs, nous sommes là pour te guider, mais ma foi, tu as été plutôt autonome. Et des fois, tu avais des idées bien arrêtées, ok, mais c'était très bien, c'est normal. Et c'est ce qu'il faut. Tu as montré une belle maturité. Je crois que tu es parfaitement maintenant prête pour une carrière autonome en recherche. Alors, je voudrais juste insister sur 2-3 points dans cette thèse. Alors, tout d'abord, c'est une thèse effectivement pluridisciplinaire. Tu as su développer des compétences à la fois dans l'analyse des observations et aussi dans des manips de labo, ce qui est quand même assez remarquable. Cette thèse, on pense souvent à de la recherche, mais tu as fait aussi de l'enseignement, tu l'as dit, et tu as aussi fait de la diffusion des savoirs. Donc ça aussi, il faut le souligner, parce que tu as pris finalement du temps sur ton projet de recherche pour faire des choses qui sont vraiment importantes finalement dans une carrière de chercheuse, c'est de pouvoir enseigner, partager ses connaissances et aussi les partager avec le grand public. Et ça, je peux en témoigner. On a fait cette tournée de vulgarisation en Guyane et tu as excellé dans cet aspect-là. Et puis, finalement, comme l'a dit Sébastien, je voudrais encore le souligner, tu as pu aussi nouer des collaborations en dehors de ton cercle très, très proche. Et je remercie aussi Sébastien sur cette collaboration long terme, hein, puisque ça fait 15 ans qu'on mène ce projet. Je voudrais aussi remercier Rosario et Kathleen pour avoir apporté leur expertise sur des aspects que nous, on ne maîtrise pas. Et contribution, Antonin et Mireia, parce que vous avez eu des discussions très intéressantes entre vous et vous avez aussi progressé par vous-même, notamment les derniers jours, avoir fait des manifs de labo pour terminer. Donc, félicitations. Et
Merci.
Okay, I just switch back to English for a few words. I don't know if you know, but your research is very far from my research domain, which is on relativity tests. So, okay, but I want to congratulate you because I've learned a lot by reading your manuscript. Very clear, very well illustrated, as it has been already said. And thank you for your presentation. That was very clear also and pedagogical. So thank you very much. I had a couple of naive questions, but you have already answered them. I just want to precise few points. The first one is the timeline of your thesis. How can you tell me what amount of time you do have spent on data analysis and on lab experiment? It was half part roughly, or it was very different? I don't know.
I think at the end it was close to half-half. So I started during the internship working about the remote sensing data and calories, and then during the first year of PhD. However, during this time, I was also preparing for laboratory measurements about the nature of the sample. We did already a first meeting to plan everything. Then at the beginning of the second year, we started the laboratory measurement with Kathleen and Rosario. So we had few days of sample preparation. We did few tests to see how we could press the sample and so on. And then it was, I think, a bit more than 1 week of irradiation. Then we had then few months and we did the mid-infrared measurement in 1 day. And then 1 year after, so beginning of the last year, we had our second week of a campaign of irradiation. But, and then so same few weeks after the mid-infrared measurement. So everything was a bit at the same time, I would say, because so I worked on the lab, but I also continued developing the methodology for the comparison of the basin. Yeah, and we stopped the lab at the end of 2023.
Okay, quite impressive. Thank you. And just to have precision about something you wrote at the corner of the slide, you say very quickly that your results could be useful for other part of the solar system or the corps. So do you have something, or other bodies, sorry. So do you have something in mind more precise, or is it just a way to open the questions?
No, so I have something in mind about silicate. So to stay close to Mercury with the upcoming ERA mission, for example. So the mission will analyze an impacted asteroid that was impacted a few years ago. So we will have access directly to properties of space weathering. So this, for example, with a small body could be directly linked. And I also put that because not the result necessarily, but the methodology in doing both lab and remote sensing is also very useful to prepare also MMX mission from JAXA, so small bodies again. So it's something I would be very interested to pursue in the future, even if it's not on Mercury, but keeping this process on other targets.
Okay, so thank you very much. That's all for me.
Thank you.
So the question session is finished, and we ask people